Am I
Yes.
audible, sir?
Yes, yes. Speak.
Sir, I have submitted my assignment. So how I can get to know whether there is any changes in my assignment? Whether I have
Change.
submitted the right document or what? So
Yeah,
I
yeah,
want.
yes. Yes, if you have filled up the form, definitely I will get it. I think, yeah, I have seen your name there. Yes.
Okay, sir. There is no changes, right?
Changes means what kind of changes are you talking about?
No, I have submitted the right document as per your document. I have designed that couple right.
Okay,
So,
okay, okay. Mm-hmm.
so
Okay,
in
okay.
that
So
any
that,
changes
no, no,
is
yeah,
required.
that I will look into later. Yeah, yeah. But
Yeah.
if you have done, that is fine. You have done the layout also, right?
Yes, sir. I have done the layout also.
Okay, okay, okay. Yeah, that is
Oh,
fine. Yes, fine.
okay.
Okay. And some other guy also has mailed me. I think Kostov or someone. Yeah, I have received your document also through mail. Yeah, is Kostov present here? Okay. So I think you also have noticed that I have posted the assignment 2 on filter design. Everybody has got it, right? Through mail. I did not post in Teams separately because I thought the mail will go to everyone. All here have seen the second assignment, right?
Yes, sir.
Yes,
We
sir.
got it.
Okay, okay, okay,
Yes.
okay. Okay. So, yeah, today I will show you the similar things here through ADS, and you can try yourself next week. Yes.
Actually, in Kaplar previous assignment, I have done the assignment, but the problem is that I have done the schematic and layout,
Mm-hmm.
but my graph is not coming properly as the PDF as have in PDF, but my graph is not have properly coming. I have
Did
checked
did did you
that.
use the same substrate?
Yes, microstrip line. I have used microstrip line and what else?
No, no, I am saying, did you use the Rogers substrate and the given loss and permittivity, everything has to match. Then only you can get similar response.
Okay.
Yeah, so that
Uh,
you can check again. Yes.
For me, hello.
Yes, yes,
For
yes.
me, symbol is not coming actually. That yellow
Symbol
color,
is. Mhm.
yellow
Mm,
color, so lightly it is coming actually.
You can present your screen so that I will know. You can, if you have your simulation settings now with you, you can show me. I can see what is the problem. Yeah,
How can I
just
present this one? How can I
uh,
present?
you can present, or you just post a picture here in the comment section. I will take a snapshot and post also.
I already submitted my picture in WhatsApp group.
Hmm.
Once
Okay,
check, sir. Once check.
okay. So I don't know. Can you try presenting? Is that option not here?
Uh, where can I find that option?
On the top right, you will have the
Share,
option for, yes, yes.
share,
Ah,
screen, window or
screen,
screen.
screen, anything is fine. Yeah, screen. Yeah, I can see. Yes. So I suppose you have followed the same steps I have shown, right?
Yes, like this it is coming actually. Yes,
Oh,
exactly.
that is fine. If the only color is faded, that is fine. I don't know that you might have changed some settings, that's why. But are the results coming? That is the important thing.
Result is coming. Result is coming. This is not
Okay,
even.
okay, okay. So while importing the symbol, they will give you some options. Okay. So if you go
What
to,
is
yeah, generate
what is the
symbols.
option? Okay, may I know what is
Oh,
the options?
okay, okay. Oh, even here also it is different, huh? Yeah, here also it is not supposed to be this color. It should be like red color. Oh, you see,
Okay.
if you notice, the same color has come to the symbol, right? So you have to
Okay.
change the color here. You can just, change the color, right click and see the metal option. You just select on one of the component here. microstrip line. Click on one of them and see there we will have some in the settings only you can select for yes, somewhere here you will see the
I
this
think it is there in the options. Options.
yeah, so that here only you can find out. Okay, if you change this
Options.
color,
Options.
yeah,
And
yes.
then you need to check all the. Actually, I forgot here, but somewhere here only.
No. In layer, in the extreme left, you can find the layers.
Yeah, conductor layer you go
There,
left.
yeah, there you can see.
In the left side, you go to left side layer.
Okay.
Yeah, either conductor or conductor 2. Yes. Here you
Conductor
select
2. Already it is all selected. No.
no change. You
That
can
is
change the
just
colors.
visibility actually.
No, you
How
can't fill.
come?
But anyway, see, I think this is not a big problem. You can do it on your own time. Okay, we will go to other things. Okay, please answer.
sure.
Yeah.
Sir, just
How
one
can
question.
Yes.
Sir, actually, I'm done with the conventional coupler, but the design that you have mentioned in that paper, so I'm not done with that. So can I submit it within by tomorrow or day after tomorrow?
Yeah. Who is speaking? I did not get your name.
Vaibhav. Vaibhav, sir.
Yeah.
Yes,
You
sir.
can do it. Yes, you can do it. Yes.
Okay, sir. So I will submit it once
Ah.
I'm done with that final simulation.
Yeah. See, even the deadline is there. I will suggest all of you to do it. It's basically for your own learning. It's nothing. It's not a,
Yes, sir.
not a degree course or something, right? Yeah. You can submit it. Yes.
Yes, sir. Yes, sir. Thank you, sir.
Okay. Anybody else?
Sir, I have submitted the assignment 1. Have you received it?
See, if you submit,
Uh,
I will get it, right? There is no in between, no loophole here, right? This is
Okay, sir.
Kaustubh, huh? Yes. I just now, sometimes back, I was asking, yeah, I have received it. Yes. Yeah. Okay. Next.
Sir, have you received it?
Yes, I got it. Yes.
Okay, sir.
Yeah. Ganesh?
That you suggested for that bend used to double bend, right?
Yes.
One on left and one on right, but still I am not able to get it.
Get it means get the results, right? What are you not getting?
Okay, let me try again because
Yeah,
that angle was 53 and another was 43, na? That curvature, how to get it?
See, that's why I have taught you guys to tuning also, right? So you may not get exactly same thing. You have to tune a little bit, right? You have to play with the results, right? You can do that. Yeah. So you will learn by, doing all these things. If everything works at the first time only, how is going to work? Yeah. Okay.
Okay, I'll make that corrections and submit it. Okay.
Okay. No problem. Yes. Yeah. Anybody else?
Sir,
One by one. Rajender, yes.
No, I don't have any questions.
Okay. You mute yourself. Yes. Pooja. Yes. Pooja has raised hand. Yes. I don't know. I can't hear you. You may try logging out and logging in again. Okay. In between, Sarojit. Yes.
Yes, sir. Sir, in the assignment, we have to done the schematic and layout and graph. Just three things, na?
Which one are you talking? First one or second one?
No, first one. For the first one.
Yes. You have to do all schematic, layout, and co-simulation. Yes.
Okay, but my schematic, my layout was the different. My in AWR, my layout has different view from the Ganesh was presenting. My layout was totally different.
That is fine. See, difference in software there might be some difference, but final outcome should be same, right? Yeah, so
Okay.
you are saying you might not have the symbol view and all this. Okay, you final, yeah, you can submit the final results coming from the final layout. That would be sufficient then.
Okay.
But
And for the
schematic,
next,
yeah, schematic you will definitely have, and you will have some other things for your layout. You do both of this. Okay.
okay. And the for next assignment, we have to done the same thing: layout, schematic, and graph.
Yeah, that you see, if I have specifically mentioned for each of the sub questions which has to be done. You look at it, carefully. I have mentioned it specifically.
Okay. Okay, sir. Thank you.
Yeah. Anybody else? Who else? Somebody is still raising hand. Who is it? Sumit. Huh.
Yes, sir.
Yes.
I actually tried to replicate the same design from the paper, but my design is resonating at 2.15 gigahertz rather than on 2 properly. So,
Yeah, see, that is very general actually. So even if you do same things, there will be some minute changes. Okay. So generally
yeah.
you have to tune things. That's why, I have showed you how to tune circuit. So the normal circuit rule is if you increase the length of a circuit, the generally resonant frequency reduces. Okay. It is inversely proportional to the length. So that's why
Okay.
you can just, increase the length little bit and you can see if that reduces your resonant frequency.
Sir, if you don't mind, I would like to share my screen and um show my layout, whatever has been generated.
Okay. Yeah, do it quickly. Yes.
Yeah. Is it visible, sir?
Yeah, it's coming up. Yeah, I can see it.
So I had drawn a schematic, something like this.
Mm-hmm.
Okay.
Right.
And the layout that has been realized is something like this.
See, that's why I guess you have used a junction or bend, something like that. What is this? So this width has to match, right? The
Yeah.
width.
So these are being calculated from the line calculator based on whatever impedance is there at the input and output.
See. No. See, the problem is the width you have taken in one place mil and another place in millimeter. Don't do all these mistakes. It just, unnecessarily complicates things. Take same unit everywhere. Okay. You see somewhere you have taken in mil.
The curves,
And
yeah, curves are in mils, and what do you call these ones are in mm. All of them.
Yes, the curve width has to match with the microstrip width.
Okay.
Yeah, then only it will go through, like it will be smooth.
Okay.
Yeah, I think you
I
do
will
it
try.
and then see. And I guess
Yeah.
I will suggest Ganesh also you see that how he has done. Okay, and next is HK Arora. Yeah.
Hello, hi, Saurabh.
Yes,
Sir,
yes.
please, can you please see my results? I also want to
Mm-hmm.
show you.
Yeah, sure. Do it quickly, yeah. Then I will go to next class.
Is it visible?
Yes.
So
Yeah,
basically,
yeah, speak.
I've basically created schematic and
Mm-hmm.
then proceed to layout. And then
Mm-hmm.
after did EM simulation, and these are the results I got.
These are the EM simulation, but you should go to co-simulation also. Okay. Anyway, it
Okay.
will be similar here because you don't have any lumped components, I suppose. Okay. So then what is the problem? Yes.
So just wanted to check out if these are okay.
These are okay, but generally you should go to co-simulation also. Okay. You try that
Okay.
also. Yes.
Okay.
Because in many of the cases you will have lumped components. So there you need to use schematic as well as layout together. Okay. Yeah.
I
Yes.
wanted to know the concept of that some people are using bends. I'll show you my schematic also. Just a second. Is it visible?
It's coming up. Not yet.
Okay. Now?
Not yet.
Should I share it again?
I think you have shared one particular screen. Yeah, that's why it's not coming.
Okay. Just give us a minute. So here I've used angle 90 degree. So some people are using some different angles. So
Yes. Yeah.
why we are using different angle?
See, there is no hard and fast rule here. You have to little bit do tuning and all here. As long as it works out, it is fine. Yes. There is no rule particularly that this is. But if you go actually, just click on one of the component, one of the bends. Click on it, double click. Now go to help. Go to help. I think I cannot see it, but if you go inside the help page, you see there will be some restriction on the bend and all. There is a equation there, right?
Yes.
Inequality equation. Yeah. So that you have to follow generally. Okay.
Okay. Thank you.
Okay.
Thank you so much.
Okay. Next, who else has problem?
When we have to put 90 degrees, when we have to put 180 degrees.
Sorry, come again.
When we have to put 90 degrees, if the length is lambda by 4 means okay 90 degrees. Without that length, we can put 180 degrees only.
No. See, there is no such rule. But generally, if you look into, as I said to her, there is a inequality equation. You cannot just use anything. There is a upper bound and lower bound that you have to follow. But as long as the results come, it is fine. There is no, in the coupler theory, you will not have anything linked to the bend angle. Okay, there is no linking there.
No. I am not talking about bends. Just I am telling 90 degrees we are taking now. For example, we will take power divider. After middle of the resistor, we will take as the lambda by 4.
Oh, okay. So you are suggesting to her, right? Understand. Okay.
No. Lambda by 4.
Yeah, I will suggest that you guys have a WhatsApp group, or you can even post in the Teams. Okay, it will just
No,
delay.
not I am suggested. No, not I am suggested to anyone, sir. Just I am asking my doubt. Okay. Lambda by 4. For 50 ohm line, how much degrees I have to take, sir?
No, that is what I'm saying. No, there is no such rule for anything. What works out, you have to find out. Okay, that because that's why it's.
He's asking about that
I
electrical
think
length.
he's
of this.
asking about port length. I think.
Electrical length, right?
No. Length not lambda by 2, lambda by 4 we are writing now.
No, I think he's asking about port length, which is 50 ohm
yes,
line.
port
So,
length. 50 ohm.
Okay. Not bend. Port length you're asking.
Yes, length can be anything. It is up to you. Depends on size of this system or whatever. It can be anything. Basically, the impedance should be 50 ohm.
Right. Yes. Okay, yeah, that is the rule. Generally, you can take a small amount of length, like lambda by 10 or something, lambda by 5, whatever. That won't matter much. Okay. So if you take very short length, it might, in the hardware, it might affect because of discontinuities or the changes in SMA connector. Otherwise, in your simulation, you will see it will not matter much. Okay.
Okay, thank you.
Yeah. Anybody else? Okay. Then yeah.
Sir, actually, in the first assignment, I have not done the code simulation part. So can I do it and resubmit it?
Yeah, yes, you can do it. Yes, add it. Yeah, I will suggest to all only that everybody please complete with up to co-simulation. Everything you do. Okay. I think I have seen 1 or 2 with only circuit or schematic simulation. That is not enough. Circuit simulation is good for only UG level. Okay. Here microwave, you have to do layout.
Sir, actually, means co-simulation is done if there is a lumped component.
If lump component is there, then it is mandatory and the results will change because in layout you cannot include. the lumped components, right?
Okay.
But if there is no lumped component, it is same. You will get almost same results. Okay. Yeah. But still for your
Okay.
learning, I will suggest you do all the steps.
Okay. So if there is no lumped component, then co-simulation is not done.
Not required.
Okay. Okay, sir.
Yes.
Okay, sir.
Okay.
Thank you.
Okay. Yes. Anybody else? Okay. And I will suggest that, you know, some of you have sent me messages in WhatsApp and all. See, I will suggest you please don't do that. Just send me mails. That would be sufficient, or post message it in Teams, this group only. Okay. Yeah. Okay. Then I will go to the next one.
Hello, sir.
Yes, yes.
Sir, I did a schematic simulation as well as layout simulation. I am using AWR for the assignments. Can you tell me about the co-simulation, how it has to be done in AWR? I tried to find out on my own, but I could not. There's no lumped element in the first assignment as it is, and you showed with the Wilkinson power divider, and I tried some idea from there, but I could not get co-simulation thing in the AWR. So can you just tell me if you have free, like at the end of the class or sometime?
See, I have not personally used AWR, so I will not know. Okay, but there must be some way to do that. Okay, you may search in Google. I guess some other people also have, you know, used AWR here, so you can just, you know, have a discussion among yourselves. Okay, I personally I have not used it, so you have to find out yourselves. Okay, yeah. But there
No,
must be
sir,
some
we are
step.
using AWR, but here haven't any option to co-simulation or something like that. We have same problem.
See, their name might be different, right? So how do you design a Wilkinson power divider there? How to do that? There must be some way, right?
There actually no separate thing is required for co-simulation. Just we create the once the EM layout is created, we create a symbol out of that, and then we place it in a regular schematic, add the lumped elements, and then we can do it. So no separate simulation setup as an ADS is required to do it in AWR.
Okay, that is fine. Yeah, that is fine. That is fine. If that includes the layout results as well as the lumped components. So you are saying in the layout itself, the lumped will be included, lumped component, huh?
No, not in the layout. So once we design the EM layout, we can create a symbol out of that. That part is similar to ADS. But after that, here when we do the simulation setup, here as we need to do the co-simulation setup, there it is not required.
Can you share your screen and show them once? That will be helpful.
In this system, it is not there. But if someone shares, then I can help them. But currently in this system, I am not having the AWS.
Yeah. So yeah, Pooja or Sarojit, can you share your screen? He might, you know, show. Yes.
I can see. Okay, so 1 minute.
Yeah, we still cannot see your screen. You can share one screen and then open. Hello? Yeah. Okay. Now I can see. Yes. See here, there should not be any overlap between lines. You are having multiple overlaps. That should not be here. Okay. That means there is something wrong. Okay. So by the way, yeah, coming back to the other thing now, Swastik, can you show how to do that?
Yes, one window is missing here. Pooja, please go to the view option on the top. There is a lag, I guess. Is the drop down visible to you? Because it's not getting reflected here.
Actually, you have to share your screen only.
Yeah, because the view options are not available. Actually, one project browser window has to be opened besides it. So in that, the options will be there. Yeah, correct. So here, if you go down, there is an option called symbol generator. You can scroll down over there. In the widget section, widgets. No, widgets. Yeah. There is a plus sign. Symbol generator you can find. Second last. Yeah. You can double click on that. Another window must have opened on of the symbol generator, right?
No, there is no window.
It will open, then maybe it's a bit slow. So another window will open. There you can select the source. It will create a sample out of that.
Yeah, I think this schematic 2.2 has opened, right?
Schematic is there already. I copy pasted from here. But the thing is, I tried to do as he said, symbol generator, then I created, but I think it is opening. It's getting blocked.
Yeah, it will open. Another widget it will open. So there you can create a sample.
So okay, then you know the steps and you can try, and maybe you can contact him later.
Sir,
Yeah.
it's not overlapping actually. I have created T-shaped band. I can show you in the schematic. At every junction, I have done this T shape. So the T shape is actually coming as a small blocks. That's why it is looking like I have overlapped multiple sections, which is not. And this actually, as per the help guidance I saw in the AWR, has to be connected in the middle of this line because it was connected with the red dotted lines. That's why I got. And if I'll separate the, you can see also if I'll separate, like I'll distance the part, these are the blocks actually. So these are the T sections which I have created at every triple junction points.
No, see, it can be better. If you see the layout in the paper, you have to actually use two of the bends in each here. Okay, then it will align perfectly. You used only one, that's why it's not aligning properly. Okay, so that's why it's
two curved bends.
Somebody showed sometimes back, if you see, remember, two bends in opposite direction, then it will, match properly.
Okay, sir. Can I redo and again can I submit by today?
Yes, no problem.
Okay, sir.
Okay,
Thank you, sir.
yeah, okay. Then unshare and we'll go to the next class.
Sure.
Okay. Okay, so last week we have seen the theory portion of the filter design, right? So first thing what we have seen, the normal low pass filter theory, the simplest one is the constant K section, what we call. Okay, so if you remember the design steps and the alpha beta plots with respect to frequency looks like this that we have discussed, and there were some problems, and because there was not a good roll up, we needed another pole near the cutoff frequency, and that will generate a good roll up, right? And that was called M derived low pass filter. Okay, and the circuits look like this. So if I show you one circuit here in ADS, so see, very simple circuit. If you just take a third order filter, it will look like this. Okay, LC, simple filter like this. And the values, how do we get? If you remember, the L and C values here is given. There is some equation here. So first thing is omega C. Omega C is the cutoff frequency. That will be already mentioned in your design problem, right? What cutoff frequency you have to design for. And then the next thing comes, like what would be the order of your filter, right? That will depend on how much roll up you want or how much the passband ripples is required. So those will decide how much, what is the order of your filter. Once that is decided, cutoff frequency and order of filter is decided, then you have to decide on the components L and C, right? So, in the very simplest case, you can just use this and the equations given here, R naught and omega C, all this is okay. But if you go to a little bit complex design, so how do you do? If you remember, I have shown you in a Poser book or any other book, there will be a table given. So one for the normal Butterworth filter, one for the Chebyshev filter, and others also. So what will they give? They will give for a normalized cutoff frequency, that means omega C equals 1, and they will tell for a particular order n1, n2, n3, I mean n given 1, 2, 3, 4, 5, what should be the components. So these components, if you remember, these are not L and C values as on picofarad or Henry or nano Henry. They will give you a normalized value. So from that normalized value, your task is to calculate what should be the actual L and C. Okay, so once that you get, then you can just simulate the circuit here, very easily. So like this. And if you remember that normalization process takes care of the omega C. Let's say you have to design here 4 gigahertz or some other frequency. You have to just take care of that normalization. And if you have other components like the port termination resistance are defined, or like source resistances as what is said there, those are different. That also you have to multiply there. That was in the theory. Okay, so similarly, once that you get, the first question was, if you remember, that was design a normal constant K section. Okay, so constant K section is, as you know, it is very one of the simplest types. Just first order you can do like this. Okay, L and C values you calculate, and the calculation I am not showing this because this is very simple, you can do yourself only thing you have to know the cutoff frequency and the order of filter, and from there you can calculate your components, and you can use this equation also here. And then the next question comes, if you have to do a M derived filter, that is also one of the question. So instead of writing M derived, or instead of asking M derived, what was asked, that can you introduce a pole near 6 gigahertz? I think that was mentioned in the question. So there we are talking about this, this frequency here, omega infinite. If you see this here, this omega infinite here, that is the next pole we are introducing by adding this M derived filter section. Okay. So that will be the next question. So how do you do this? For that, you have to, use this function M. So once omega infinite is already mentioned in the question, omega C is given, you can calculate M. And for calculating M, there are two sections. One is for sharp cutoff, that is improving the roll up. Another is for matching section. Okay, that we are coming to later. And once you know the M, you can calculate these components here, L and C. L and C's initial components you know already from here, the first constant K section. Then you multiply this M constant here and get these components, right? So once these are done, you can just design simply. So this is the section C. The left one is the constant K section and right one is the M derived section. And if you see the responses here, is clearly visible. It shows that M derived section you have a very sharp roll up. Okay, you see, because around 2 gigahertz this extra pole was introduced here. Here omega infinite is around 2 gigahertz, and I will show you in the ADS also. So this was the constant M section, and that response here is here. So if you see, this is the S21 plot, and you see S21, it was designed for 1.8 gigahertz and minus 3 dB. That is the cutoff frequency 1.8 gigahertz. That matches. So this also you should plot in your results. You should show that your cutoff frequency actually is minus 3 dB below. Okay. And if you see, the bottom one is the S11. So S11 is good at this frequency. At the stop band, it reduces. So this is K type. And then when you go to M type filter, M derived filter, this is this. Now see, there are so many additional sections. Why? That is because, so only one constant K and only one M, if you add, the matching will be affected. One of the requirements of RF design is that we should have a good matching both at the input section as well as on the output section, right? That means S11 as well as S22, both should be good for a two-port network. So for that, you need additional matching section in the both sides. If you see in this picture, this is also taken from POSAR. Left side as well as right side, we are adding two extra M-derived section for matching to ensure matching. And additionally, we have cascaded the constant K section and M derived section. So there are total now 4 sections. Okay. So now starting from only one section, we have come to a place where it is 4 sections. That's why the filter, the equation circuit here in the schematic here, you see there are 4 different sections. First one is the M, second one is constant K, third one and fourth one is again defined M. So now they will ensure attenuation as well as matching all together. Now, how do you calculate this? So that design thing comes from this equation. All comes from these two equations. Okay. So M, I told you M, there are two functions. One is 0.6 for matching and another is for the cutoff. Once you know this, you can just plug in these values here and just do the simulation in ADS. That is what is being done here. Okay, because the cutoff in this one was designed for 1.8 gigahertz cutoff, and they have done this thing. Okay, and if you see the results here, see the M derived section results. So if you see, the right one is the S21. See, we have a very sharp pole here around 2 gigahertz. Okay, that was introduced externally, additionally. So because of this M derived section, now you see how the roll-off has drastically improved. See that? And if you, so that is one of your tasks also in the second assignment, you will see yourself and the S11 is given. Okay, so this is very simple and you can just, do yourself. So is there any question until now? Okay. So if there is no question, now we'll move on to the next question might be like, so this is a first order filter, right? Low pass filter. Now let's say we have to design some third order Butterworth filter or third order Chebyshev filter. How do we do it? Okay. So in that case, so if you remember the theory, the table already gives you the values, right? As I told you, G1, G2, G4, all these component values. So from that, you just have to, calculate your capacitor and inductor values, and then you go there. Just do the simulation. Okay. If I will go to this. So this filter synthesis portion, it shows the, the table you will get from your book only. So one is, equiripple, another is the maximally flat filter or Butterworth filter, right? So for both of them, you will have separate tables. And then the important part is the scaling. The scaling you have to do properly, given on the, for your given cutoff frequency. So let's see here. So this is very simple, the third order filter where this L and C values has been calculated for a 1.8 gigahertz cutoff frequency. Okay. And the results will be here. So if you see, these results are almost similar to the maximally, the first one what we have seen, constant K type, it will be similar to that. Now, if we move to equiripple section, so filter looks the same order, okay, because it's asked to be third order filter. Okay. And the components only changes. The value of the L and C values changes. And because of that, the response also, you see, now you see the difference here. You see there is a ripple in the S21 results because it's a equiripple filter. And if you notice, the roll-off has improved compared to the Butterworth filter. Okay. So these are like very simple steps. I don't think I have to stress more on this. But later, I will focus more on the microstrip design. Okay. But you can ask me if you have any question until this.
Hello, sir.
Yes. Yes.
In ADS, you use term G as a port.
Sorry, G. Where do you see G?
In ADS, you now you see saw.
Okay.
This.
I'll show. Yes. Show me here. Yes. What are
not
you
term
saying?
G. Not term G. The term one is
yes.
Z equals to.
Term means termination one. Port termination. Yes.
Because in AWR we haven't this term, we have just port, so that's why I am asking you.
Similar. Yes.
Okay.
Yeah. Also, you can take term for terminology, right? Different for different softwares. Yes.
What is the significance S parameter also here?
Sorry, what is?
S parameter.
Oh, this is the simulation engine. If you run this through, this will only facilitate your simulation. Yes, you have to add this in ADS.
I can't see this in AWR. That's why you ask.
Okay, no. That's that I told you initially, right? I think you have joined late. You might not have attended first classes. So there will be obvious differences in all our different softwares. Yeah. Yes.
I just want to know whether it's a mistake or it is in the capacitor positive is being grounded.
No. See, these are all AC, right? RF means AC. So there it will not matter. Yes.
Okay, got it.
Yeah, right. You have to, basic circuit things always follow. Yes.
So it's in AC, so it doesn't matter, right?
Yeah, it does not matter because plus minus is changing. Yes.
So it's a AC simulation then.
It's not AC simulation. RF microwave high frequency means AC, right? What does AC mean?
Okay.
Yeah.
Okay, got it.
Yes. If you remember in basic EM circuit theory, basic EM theory, you have harmonics, right? You imply a electromagnetic wave with a sine wave, sine omega t plus theta, right? That means it's a AC wave.
Okay, got it.
So in your low pass filter design, you have used termination with impedance of 75 ohm. Why?
Which one? Here it is 50, right?
And here it is 50, but the previous design that you have showed.
Oh, that might be some, it has been tried different things. That's why.
Okay.
Yeah. So actually, because the schematics are so easy to do, you should, try out lot of things. By doing lot of things only you will learn. Okay. Yeah. You should try out different things. Yes. Yeah. Anything else? Otherwise, we'll move to microstrip light design now.
Sir, a small doubt.
Yes, sure.
Sir, actually, what is, I mean, if you're increasing the order of filter, so what is the advantage, main advantage?
See, generally, if you increase the order of filter, it improves the performance. So performance means it may be in terms of your ripple, it may be in terms of your roll-up factor. Generally, it is roll-up factor, what we have seen in this one.
Roll-up factor.
And yeah, you can also experiment. See, in the assignment, I have asked you to do fifth order, right? So you can try third order and fifth order both and compare between them.
Okay, fine.
Yes.
Okay.
And this will just take, it may take only 5 minutes. Okay, so it's not a big deal. You can do easily. Okay. Okay, then we'll move to next one. So now the main question is how to do all these designs using microstrip lines. This, right? Because that is what we are trying to do. Filter design in microwave. So, so now what will be the steps? So if you remember, in the last class, I have already discussed about the theory. So one was commensurate line theory. Okay, so in commensurate line theory, the transformation we use is called Richards transformation. So using the Richards transformation, we are able to convert a inductor by a shunted stub of lambda by 8 length, and a capacitance, we can replace a capacitance by a open stub of length lambda by 8. And because the length was same all across the lines, that's why it was called commensurate line theory. Okay. So that was one part of the theory. And next we have seen that some of the cases it might not be appropriate, or it might not be feasible to just insert somewhere a series or shunt stub. In that case, we have to do a additional modification. So that in there we had a theory called Kuroda's identity. So Kuroda's identity helps us in transforming open stub to short stub, or vice versa. Okay, there are 4 Kuroda's identities, and all of them are very useful. Okay, so those we will see now. How it is actually used in the filter design. So let's say here we wanted this example also is taken from the Poser book. So I will explain you step by step how it is done. So let's say we start from the first step here, the lambda element prototype. So that you have already done. Let's say we start from a Butterworth filter of third order. We know the components. We decide on the L1, L3 and LC2. These are known. Now our task is how to replace this L to L capacitor inductor with a microstrip line section. Okay, so first thing, what do we do? Use Richards transformation. Okay, so from there we know the length of the line is easily known, that is lambda by 8. And now the impedance of the line you can calculate using Richards transformation for the shunt. That if you remember, I will show you again for you so that you remember. I will show you the theory again. Yeah. So from here, if you remember, you can calculate your Z0. That means the characteristic impedance of the line using these formulas. Okay. For a given L and C, what should be your characteristic impedance? Once you decide that, and you should remember the length is lambda by 8 at cutoff frequency. Okay. So you have to determine this length at which frequency, none other than cutoff frequency. So this is the first part using Richards transformation. Now coming back to this. So here in C, second step, the L has been replaced by the let me take the pointer. So L has been replaced by the shunted stub here. Okay, the inductor. And then the in between the capacitor has been replaced by a open stub. Okay. And again the third L is symmetrical, has been replaced by a another shunted stub. Now if you see that adding a series stub here in between is very difficult. Okay, so we need to do something here. So for that, what is required is Kuroda's identity. Okay, so second Kuroda's identity says in this right side picture, if you see a impedance line of some impedance Z2 and here it has a, it is a shunted section. Together, it can be replaced by a line section of characteristic impedance KZ1 and one open circuit, open stub of impedance KZ2. This K factor, if you remember, is it was called there in theory N. So it comes from N square equals 1 plus Z2 by Z1. So that is the theory. So that you know and easily. Z1, Z2 known. So from that ratio, you can know the K. So this is the second Kuroda's identity. So for that, so we see here we have added an extra line section at the beginning as well as at the end. These lines are also lambda by 8 and Z naught is 1. So here if you if you notice all the Z naught is 1, 2, 3. These are not actual impedance. These are normalized with respect to 50 ohm. Okay. So coming back to the Richards, to replace this section with Kuroda's identity, you need extra additional length. Okay, for that, if we add at the beginning or at the end, here at the beginning, at the end, if we add a additional lambda by 8 section of 50 ohm line, it will not change actually any response because it will be matched to input side as well as to the output side. So that we add this additional, see, this L1 is only this shunt, but this extra additional length we have added so that we can replace this whole thing with the Kuroda section in the here using Kuroda's identity in section 3. Okay, so now if you see, we have replaced this whole thing here, this line length as well as the shunt. Using here, you see what we have added a open circuit stub along with a defined line length. Defined line with a defined characteristic impedance that comes from here KZ1, KZ2. This exactly shows here this section. Okay, so this line as connected with this shunt stub is replaced by a open stub connected with the line. And this now see, because it's a open stub, is very easy to connect. Okay, but because in the previous case it was shunted stub, we could not have connected in series. That was the problem. Now that we do this same thing here also, because it's symmetric, the third section also replace, and the in-between capacitor remains same because open stub we can connect easily. So that remains same. And here you should notice this all the lengths are lambda by 8. And that omega is 1. Omega is 1 means the cutoff frequency 1, that is normalized. Now if you have to, the next step is what? You should get rid of your normalizations. How do you do it? All the characteristic impedance of Z, you just multiply with 50. That is done. And the length you have to calculate as lambda by 8 at 4 gigahertz. Now 4 gigahertz is what? That is the cutoff frequency here. So accordingly, you have to calculate your line length. All are lambda by 8 except the port length. At the beginning, at the end, there are some port lengths. Just similar to what you have seen in your previous assignment also. Always in microstrip line circuits, you have to add some line length per port. These lengths are all, again, there is no such hard and fast rule. You can take some length, some small amount of length, and then connect your termination impedances and source all together. Okay, but what comes in between this open circuited and short circuited is the design rule. It is designed accordingly. Now at the final section is is finally what the layout looks like. If you also design your assignment, it should be looking like this, the layout. How it comes, see, the 50 ohm line is the port line, is this section. Okay, this and this. And then comes the open circuited length. This is this open circuit 64.9 ohm. Then we have a different microstrip line section, comes from the Kuroda's identity. We have another open section representing the capacitor here, and then again together this open stub and the line representing the L3 inductor. And then again we have another 50 ohm line for the port connection. So that brings us from the initial first step to the fifth step. All these steps you have to do one by one to get it here. Okay. So what you have to do, you have to just follow the Richards transformation and Kuroda's transformation. You have to do some small maths. You can do it in MATLAB or any calculation, or you can do in pen and paper also. Okay. Now, yeah, I will show you some simulations on this. So similarly in ADS, we have designed So the same equiripple filter or the same flat maximally flat filter we have designed so far, the same we will try to replace using the using this transformation theory. Okay, so schematic is, as usual, you can just take a transmission line, all this, open sort is very usual, and what you have to calculate is, if you remember, the impedances, right? Once you know the characteristic impedance, what do you have to design it for a transmission line? It is just the width, line width, because you will already have your substrate thickness is known, okay, permittivity is known. Once all these are given, for a given impedance, characteristic impedance, what you need to know is the width of the line. Okay, once this characteristic impedance known, you can use the line cal tool and calculate the width, line width. So that is what has been done in this design. Okay, so I needed something for 1.8 gigahertz. This is one thing. I think the other one is okay. This one, yes. So this has been done here. The same line length and width. The T section is obviously required for the connection. And this section here, you see, it has been just kept open because it's open circuit. Otherwise, you can take a open circuited line also. That option is also there. Or you can just keep it open. Okay, that is also another possibility. So if you go to the transmission line components, yeah, so here you see there are normal microstrip lines as well as there is the open circuit and short circuit. These options are there. Now because here we need open circuits, these lines you can replace by open circuits here, these things here. Okay, that is also another possibility. So again, what you need from here is the line width and length. Okay, line length is given by lambda by 8 as usual for your cutoff frequency, and width is what you have to calculate using your line cal tool. So once these are given, you can just simulate. The components comes just from your design steps here. You shown one by one you have to follow and then come back here in the fifth step. Once this is known, you can just do it here. Okay, and that is nothing a big deal. And as usual, you can do some tuning here, length and width, all this you can play with it little bit. So there will be all these fringing components and all this, so theory might not exactly follow. You might have some little bit of changing here and there, so you have to do playing some tuning and all, so that you get your cutoff frequency and roll off whatever you want. But motamoti it will follow. Okay. So yeah, that is the thing. Now if you see the simulation results from this, this is schematic. The schematic I have shown you here. Now if you generate the layout, it looks like this. Okay, this is exactly what it was showing in book also, right? See, this is how it looks. Okay, the ports you get here, and these are the open stubs. You see, this is one open stub, this is another open stub, this is another open stub. These two are 50 ohm line section, and these are in between lines what has been added because of the Kuroda's identity. Okay, that is what you should get similarly. Now this in between squares comes from the meshing because it has been simulated already, and the symbol will come like this. Okay, the same steps you follow here and get the ports. Now what do you get here? The results will give you, yeah, so you will get results like this. Okay, these are the S212 and S21 results, and S11 results will be like this. So because this one was a equiripple filter, so you see there is some ripple here. Okay, this was a third order equiripple filter designed with commensurate line theory. Okay, so this is that. You can also design any other filter like, Butterworth or any other design, but the rules are same. Okay. And I think in the assignment you have been asked to do the same equiripple filter only. You can follow the same steps. Okay, so this is the one part. Now, do you have any question on this? Yeah, do you have any question on these design steps?
Sir,
Ah.
sir, I have doubt from third to fourth step in this slide. Means I want to ask, like we have converted that section to this Z1 and KZ2, that one. And then third step is converted. In fourth step, I'm not able to understand how that Z0 4.3 changed to
Is
fourth
just
step.
multiplied by 50. See, in these cases, the
Okay.
Z0 has been, normalized with 50 ohm resistance. Okay. So that's why
Okay.
you have to multiply with 50.
Okay. And then do we have to find that K factor also here?
Yes. Obviously, this K factor is required to calculate this. That is definite. Yes. Because otherwise you don't know, right? The K comes from, if you remember from theory, I'll show you.
Yeah.
Yeah, CK here. It comes 1 plus Z2 by Z1. Okay. We are actually talking about the second one here. This is the second one. Okay. This is what we are actually using. Okay. So here you see L was in the first and then line, and then we are representing with a line here and then capacitance. Yeah. So this the N is given here. I think this 1 plus Z2 by Z1. It will be N square. Yeah, this formula is wrong. It would be N square. Okay. Yeah.
Okay.
Yeah. So this you have to
So
calculate.
that is okay.
Yes.
So that N square is K basically.
N square is K. Yes, right.
Okay.
Yeah. So that's why you are required to look into the Kuroda's identity theory once. Last week I have showed you, right? You just go through this once and then you will understand. Yes.
Okay.
Actually, you have
Hello,
to
sir.
use your. Yes. Go.
Sir, I have a question, sir. Actually,
Yes,
at
tell.
some point you have said that the length of these lines, microstrip lines, it should be equals to lambda by 8.
Yes.
Okay, so
Lambda by 8.
so sir, I haven't got that point because widths we are going to calculate by using the impedance that we have found and by using the line calc tool, isn't it?
Yes. Right.
But how to find that length, sir? So can you explain it with some examples, sir?
Oh, this is simple, right? See, lambda by 8, if the cutoff frequency is 4 gigahertz, you can find out lambda from there. This lambda comes from cutoff frequency. Yes.
So that will be the lengths will be constant throughout these you can say the elements.
See, this comes from, if you remember the theory, from Richards transformation and Kuroda's identity. So that's why it's called commensurate lines. If you remember, commensurate lines means all these line sections are same length of lambda by 8.
Okay.
This is not
Okay,
given
sir.
by me. Is the theory says what? Yes.
Okay, sir. Sorry for that. I was confused about that.
Okay, no problem.
Okay.
Yes.
Sir, in power divider, we are calculating length by using the line cal, correct?
Yes.
And it is a lambda by 4. Correct.
Yes.
So if you are using the same line cal for lambda by 8, how it will calculate, sir?
You know, right? If you know the line with line characteristic impedance, so you can put lambda by 8 means what? What angle? That means lambda by 8 means how much angle? 45-degree angle, right? So you have to put the electric length equals 45 degree and it will give you the length. Or you can just use pen and paper, right? It's not a big deal. You can use pen and paper only.
No, I'm just asking for power divider, you are using lambda by 4. So here we are using lambda by 8. So that's I got
the theories are different. No. The theories are different. There is no relation with power divider here.
Okay.
Yes.
Okay.
Okay. Anybody else?
Hello, sir.
Yes, yes.
Sir, I have one basic question. Actually, now we are putting everything in the schematic, then we are converting into the layout. Okay. So that since we have all the impedance requirements like 50 ohm to 17.5 ohms, so can we directly go into the layout and there we can put it?
No, there is no such design available. So then you have to just abruptly put anything and get, right? Why do you do? Because if you remember, the analog filter design or circuit filter design is well established maybe 50 years or 100 years back. Okay. So that's why we start from there and then use these things. Okay. Use these transformations. There is actually no way to, directly do in the microwave. Yes.
We can do the microstrip line, I mean, like designing without using the schematic also, right?
No. The design starts from the see. It's not like you cannot do. Then you have to optimize, do tuning. It's like blindly just throwing stones somewhere. Okay. But if you start from schematic, that means you know the theory and then you proceed.
Okay. But I think so. We can do the same directly from the layout also.
No, if you can see, you can do in 100 ways, but is there a theory available?
Yes, sir, we can do.
No, I am saying, is there a theory in the books given that you can show me? Then will be fine. Yeah, I have not seen.
No, actually here for 50 ohms, we need to calculate the trace width and its length. Okay, 50 ohm, whatever length we can use it. For 217.5 ohm, those and all must be used with lambda by 8. So lambda by 8 in the sense 360 divided by 8. So that length, if we put it, then line calculation we can get the length. Okay, so we need to have a trace width as well as a trace length. So only those two are enough to draw it in the layout. So if I'm wrong, you can correct it.
If you know length and width, we can able to draw in layout, sir.
Yes. I mean, you tell me in which of these steps you are singing that is not required. Which step? In 1, 2, 3, 4, 5. Which one?
No, in a simulation, first we are going to the schematic. Then we do the available. We are taking the available transmission lines. There we are putting impedance, these and all. Then we are converting into the layout. Okay.
Right.
So since we have a impedance trace with.
Okay. I understand. You are saying if you can see, that is like manipulating things. You will not learn. See, that's why. See, nowadays you can do without learning theory also. That is it's like throwing stones blindly. If you know the theory, it will help you. Okay, that's why you will learn the theory. Yes, there is a things available. You can just manipulate things to and modify things to that you might get there, but it's required that you learn the theory.
Okay. Also, one more doubt. Here, the line impedance 70.3 is there, no? So that in top of that transmission line, so we have to bring to the mid of the 217.5 ohm. We have to connect mid or in the edge of the 217.5 ohm. That 70.3 I'm asking.
Fine, edge is also fine.
Okay.
Yeah.
That's all, sir. Thank you so much.
Okay. So the next question is, if you remember from the theory, how to use a stepped impedance line for low pass filter design. So one of the easiest theory is using stepped impedance. But you should remember that this is used only for low pass filter. Okay, it's not available for high pass or band pass anything. So what makes it very suitable is that once again you start from the schematic. Okay, LC components. And then if you know this LC, the theory says, I will go to just theory once again so that just quickly to make you guys remember. So this stepped impedance theory, if you remember, it says a short length and large Z0 characteristic impedance gives you a inductor. And a short length with a small characteristic impedance, it works like equivalent to a capacitor. So that means high and low. It's called high-low line also. high impedance is inductor and low impedance is, it is a capacitor. So only thing what you have to calculate here is the length. The length has to be calculated. So the same thing here, we are replacing with this high and low lines. That is what we are doing here. See, here the C1, L2, C3, all these components has been, total 6 components has been divided with, has been replaced with 6 defined line and lengths with defined characteristic impedance. Now the formula, we can calculate this. The value, what is has to be calculated is the line length. And what is already given is the question, what will be given is the, let's say, the characteristic impedance, high and low. What high and what low values you want to take. If you see here, it was given 20 and 100, one case, right? So 10 and 100, and you can go like 5 and 200. These defined combinations you can take. Now there is no hard and fast rule there. It will basically depend on, if you see, it will go to the length of your, the fabrication limits. If you take very thin line or like 5 ohm line, 5 ohm characteristic impedance, the line length will be very thin. So that might, go to some millimeter or sub-millimeter. It might be difficult to fabricate. So you have to take something which is appropriate and can be fabricated. So let's say something, that's why we fix something there. Let's say we take 10 ohm and 100 ohm. 10 ohm is the low line length and ZL, and ZH is the high line impedance is 100 ohm. Now once those are known, R naught is 50 ohm, L and C we know already here, we can calculate beta L. So beta you know from the cutoff frequency again, and L you can calculate here. So that is finally L1, L2, L3 values you have to calculate. So this is that table. Okay, this is taken from POSA. There is example given. You can look into this. So if all these are knowns, you can calculate the beta L. So once the line length is known and given the impedances, you can calculate again the line width, and that will be symmetrical as you see here in this. Your layout will look like this. It is symmetrical. So line width and line length. These are the two design parameters. That is what you calculate. And then you go to simulation. Okay, so I will show one thing what we have done. Yeah, so this was a simple third order filter design. Okay, so that's why there are 3 line lengths. So one high, low, and high. Okay, so that has been used here. It comes from the same filter design. Starts from, let's say you have to design a Butterworth filter of third order, cutoff frequency given. So from that, again, you take the table on the book and then calculate the components L and C. And from there, you go to these design rules and calculate your line length and impedance line widths. Once that is done, that you can just put here. Okay. So thing is line length and widths. These are what you have to calculate. Okay. So once that is done, now what do? You generate the layout. See how it looks. Okay. Because you use third order, this is the high impedance line because that's why the width is less. And this is again, it is a low impedance line with this mode. And again, you have a high impedance line. Okay. That is how your layout look like. Once this is done, you go to symbol again and do your port and all and do the simulation. Let's see the results. Yeah, this is the EM simulation results. See, this is the S21. Okay. So as you see, it gives a S21 results like this, like a low pass filter. So there are some minute results changes in the result compared to the commensurate line, but is very easy to design and it may be very compact also. Almost okay. Okay, it's good for low pass filter only. So this is one of the other aspects of, I mean, one way to design the low pass filter. That's all. So this section is also done. Do you have, you also have one question on this section? Do you have any question on this?
Sir, I want to understand how that high impedance is related to width. High impedance means corresponding to inductor.
Mm-hmm. High impedance is correspond. Yeah, that is one way you can say. But if you actually, there is a given equation of characteristic impedance of a line, which actually relates to, the line width and line thickness. There, if you see, it is actually inversely proportional to it. Okay. There is a equation for characteristic impedance of microstrip line. There you look into this.
That W by that ratio.
Yeah,
Okay.
Yes.
Oh, okay. Thank you.
Excuse me, sir.
Yes.
Sir, the last results that you shown, that schematic, EM simulation result.
Right. Yes.
Yes, sir. So there, after 4 let's say 2 gigahertz, if I consider, then it is increasing.
Increasing, yes.
So is it like band reject kind of, or means after that frequency it is increasing?
No, it's not band reject. See, if you remember the theory again, so yeah, see the simulations. It has been shown last week also. I told you, because microstrip lines and all those are all periodic, have periodic responses. Okay, so after sometimes it will again go up and go down. If you do it even further frequency band, you will see this periodic response will come. Okay, and you can also say that it is one of the limitations of this kind of filter. You will not see the blue one shows what you get from circuit, and the red one shows what you get from the this high-low filter. But if you are only interested in this band, you see it will not matter much. If you have not, don't have a frequency component in your other transceiver which is very close to it, then it will not matter much. Okay. Yeah, so you should know about all the limitations and all. That is all about design. Okay.
Yes, sir. Thank you.
Okay, so yeah, we'll move fast now. So now these designs are done, and the next is there is high pass filter design and band pass filter design. Both of those I have asked you to do in schematic only, and that is not a big deal. Only thing is you have to high pass filter, remember the theory. You have to do the scaling only. Okay, frequency capacitor inductor will change, replace their places. And for a band pass or band stop filter also, you have to use a different transformation, the same in this theory. So that is all you can do. Start from the same G1 G2 values for a low pass filter, and then transform this according to your band pass response, or like cutoff and high frequencies, lower cutoff and higher cutoff. And then you can do this replacement in your G and K value, G multiple values, and then get the L and C. That is, you will get a L will be replaced by a resonant component like this, and C will be replaced by another resonant component like this. So that is how I will show here. It must be here somewhere. See the high pass filter, it will just look like normal low pass. Only see here the capacitance are connected in series and inductors are connected in the shunt term. There's the difference. Otherwise, it all looks like same, and the values you have to calculate using the same rule. And the response you see, it will change. Okay. So S21 you see, as you see here, it has changed with respect to the S11. It goes up after the cutoff frequency. You see, cutoff frequency again at 1.8 gigahertz is gives minus 3 dB. That you should also notice in your design. If that comes, then your design is correct. Okay, this you should follow. The cutoff frequency should be minus 3 dB. This is one part. And similarly for a bandpass filter design, now you see what I showed you in theory. Yeah, L will be replaced by a series like this, resonance circuit, L and C, and capacitor will be coming, replaced by this. And this comes from this theory. Okay, you have to calculate that. And the same thing has been done here. The same component has been replaced by this L and C components here. And you get something like this. Okay, and once you do this, and the response, let's see. The response is like this. So the response here you see is not good. I think there might be a mistake here. So yeah, I think the L components has not been. Yeah, here it might be in series. I think this component. Yeah, this will be in series. That's why it has not come. But the concept is same, and you can do it yourself. Yes. Okay, now coming back to this, so I would want to bring something to your notice that this filter design kit I have found lately. It is very useful and given by Professor Rakesh Sinha. I think you might know him. He is from NIT Rourkela. So these are available in these pages, and there is also a software available designed by them, same group. You can use this tool, download it. It's available in IEEE. It seems like you can just put the components, your cutoff frequency and all this. It may calculate your the required L and C values for you. Okay, so I have not used it personally, but I will suggest you guys use it. Download it and try to use it. And the theory is also given here. Okay, so you can just look into this how it works. All right, so this filter design kit is available, and I will suggest that. But you remember this is only for calculating the L and C values, okay? Capacitor, inductor values, not the microwave. Finally, in the microstrip line design, you have to do yourself. Okay, that I don't think is available here. But instead of calculating yourself, generally we use a MATLAB tool or something for calculating the values here. So you can use this tool. And okay, now the last section is I will cover one part of the bandpass filter. So last week I have just quickly I have given you an overview. I will go more deeper into at least one type of bandpass filter design, although it's not part of your microstrip design in your assignment, but I will give you one way to do it. Okay, so just these steps are taken from this book here. So recently I found this book on microwave filters for communication systems. It's by Richards and Kurtzia and Mansoor. So it's a recent book. You can also look into this. This is only for filter design, okay, and the theory and all very covered in depth. So what I found is they mention how to design the bandpass filter here. So one of the ways is using a gap coupled resonator. If you remember from the last week's theory, I will just go to that quickly. So this was one way to use a coupled line filter, but another way, or rather I will say it was like much more compact or easier way, is to use a gap coupled filter. So it looks like this, okay? The series connector resonator, it kind of looks like this. So the design constants is again the length, line length, and this gap. So actually, this compared to the high pass, low pass, whatever we have seen, bandpass filter design is kind of trickier, okay? And you have to do a lot of calculation to come to a actual hardware design. So we'll see some steps here. So here in this book, the steps are mentioned one by one. So first is you have to identify the filter order and filter function. Function means is like Butterworth, Chebyshev, what order filter you want. That will be generally come from your requirement or the problem or cutoff frequency. Then there are multiple ways of synthesis. So one is coupling matrix, another is K and J type inverter circuit. So the inverter circuits we have seen last week. If you remember, you just go to the theory once again. But the coupling matrix we have not seen. And if you are interested, you can look into the book. Okay, so this is, I will say, like one of the very new ways of analysis. As I see this available in nowadays in many of the papers, they use the coupling matrix theory. You can also look into it. But for now, we will look into the J-type or the admittance inverter circuit model. So then the third step is which type of hardware to use for filter design. You might use a waveguide or coaxial or a microstrip line and all this, right? But for now in this course, we are looking into microstrip filter design, right? So now when we fix all these things, what we have to do is the actual physical dimensions, like line length and width or the gap in this case. So the basic microstrip bandpass filter design using this J-type inverter, the schematic looks like this. You have multiple J-type admittance inverters connected, and you have L and C connected in between. That works like kind of a resonator. It replicates a resonator, right? That's why bandpass filter comes from. And now the circuit equations, basic circuit equations is what you get here in the right side. So these equations are very important. Basically, you have to actually calculate these equations here, solve these equations here to finally come to your physical dimensions for bandpass filter calculation. So here you have the wavelengths, like and these things here, delta comes from this value here. And what is this lambda G, G1, G2? Lambda G naught is your bandpass filter center frequency, and G1 and G2 comes from the lower and upper bands. Okay. And there and again this G1, G2, Gn, n is the order of filter, and these G values again you get from the same table based on you want a Chebyshev or Butterworth, that you get. And if you get that and your frequency is given, you have to calculate the G. J is the admittance conversion values. Once you know this, then there are further steps what I show you next to calculate actual physical values. Now see, so actual layout, it looks like this. Okay, so there are several dimensions which you have to calculate. L1, L2, L3, this length, and the gap is another constant, and then the width W here, how much is that, and then the thickness of these lengths. Okay, so now it says the most important part of this is this parts. Okay, the capacitance gap as well as this length, it can be represented by three capacitance schematically. You can represent by these three different susceptance values. Once you put this here into this circuit, you see, so this circuit looks like this. Now finally, if you replace it with the admittance values or the admittance inverter values, the schematic looks like this. This is just pure theory. Okay. And now why did we start with the like 6 gaps like this? I mean multiple gaps, because we wanted to have a 6th order filter. That is already a requirement. Okay. So 6th order filter means this one length as well as one gap together is one order. So like this, you see total there will be 6 line and 6 gap together pair. This line and gap pair is total 6. So that's why it's a 6th order bandpass filter we are designing. And see in the bottom it is given 2 gigahertz is the center frequency, bandwidth, return loss, and the microstrip line and all this. These are all mentioned already for the design. Now what do you have to calculate? This length and air gap and all these things are L, W, L0. Now what do we do? So the most tricky part is here to calculate this gap here, D. This this gap here, D4, D1, D2, D3. So this gap we have to calculate. So there is no equations what actually links directly to the what you need. Okay. So that's why 3D simulation tool or circuit simulation tool will be required. Okay. Coming back to this, So in this book, these are all taken from this book only. You can also look into it. So let's say our requirement is 6th order bandpass filter, and these are the frequency and all this. So first we calculate for 6th order filter what are the components. These components we get from a the table given in for a same low pass filter design. The same table is valid. Then from this previous equation, these equations here, what do we calculate? These J values, J0, 1, 0, 1 means 0 to 1 step, from 0th stage to first stage, what inverter is connected. Here you see 0, 1, 1, 2, 2, 3. Okay, that means 0 stage to first stage, what is the inverter connected. So these you calculate here. Okay, so for given all these values, you can calculate. Now, there is no direct equation what links this gap. So that's why in this book they have calculated, taken several different gaps and did circuit simulation as well as 3DM simulation in ADS, and they have provided a lookup table. This lookup tables, is same as what you get for your, Butterworth or Chebyshev filter lambda element components, G1, G2 values. The similar tables they have provided, they actually, made our task easier. So you can look into this. So if let's say if your D was known, you can just calculate the value here for a simple, for a simple circuit like this. You can calculate your parameter S parameter results using ADS, and you could have used these equations S1, S2 values. If this is done through Agilent 3D simulation. Calculate this and put this value here, and then from this you can go and calculate the J values. Okay. Once you know S parameter, you calculate the susceptance values. In the next stage, you could calculate the phi. Phi is the phase between the successive layers, and the admittance inversion values. Then once these are known, you could calculate the length. Length is this length, L1, L2, L3 in stages. That's why. But the problem is, because we don't know what to begin with what gap, we don't know actually. So these steps are actually hypothetical. Okay, so basically what we have to do, we have to follow this lookup table here, and we have to pick some width and L0. What L0 and W6 here, you see L0 is the length here, I mean this capacitive gap, width of this, and the width of this capacitive gap, this W and L0 they have already fixed. Okay, and then on top of that they are only calculating only the D gap. So they have actually made the task easier by fixing two things which will be same for all of them. Only the D gap and length will change. Now how do we calculate the D? So they say if these J's are required, okay, if these are the J values required, what should be the D value here and the phi value here? The D and phi are required. Okay, now how do we get the J value here? J value we can calculate here from the given things. Okay, now you have to see which value of D is closest to your J here. Okay, that is how you have to calculate. Once you get that, then your task is to find the length. Then once you get the length, you can just simply design your layout here. And this is what they have shown. That is what, their filter simulation, that also in is ADS only, what looks like. It has 2 gigahertz, and 2 gigahertz is the center frequency, and some, I think 40 megahertz bandwidth they have done. Okay. So see, this is the final table. Length and D, 1, 2, 3, 4 are the defined things, defined stages. And why only 4, not up to 6? Because the other stages are symmetric. So with respect to the center gap, these 3 and these 3 are symmetric. Okay, so here that's why you see J01 and J67, they are same, and 1, 2, 5, 6 they are same. Only J3, 4 is separate. So is the steps clear? So again I will start. First you have to decide which order filter you want. Okay, so for that you have to get the G1, G2 values from the the simple table what you get from your book. Okay, Chebyshev or Maximum Ripple filter. From that you can follow the equations here to calculate J value. Okay, J is the admittance converter value. So once these J values are done, then your task is to find, look into this table and then find what would be the length and gaps, these gaps. You can fix one width and L0 and then find out what should be the D3 and L3. So yeah, one thing you have to remember that this table might not be valid for all other designs. So you might have to do a similar, make your own table. Okay, that is also might be required. So once you know this gap is required, you can fix the gap. The phase also here, and then you go to the length calculation. Once the length is known, that is how you come back at the final design. So as you can understand, there are several steps is required here. You have to do, it requires a lot of effort. So if I just went through, I took some additional time today because of, I was going through the theory. So if some of you are, it might, help some of yours. You can look at the book yourself and read in depth. So that brings us to the end of today's session. Do you have any questions here?
Hello, sir.
Yes.
Actually, I came to know about the value of that J, but what after that, once we have got the value of that J, so what about this W equals to 6 mm and that L0 equals to 1.234 mm? So how we have calculated that value?
See, that value they have taken. Okay, so some of the cases is like there is no rule. You have to fix according to your convenience. If you are okay with 6 millimeter and 1.23, if your fabrication permits it, if your, let's say you have to design a PCB, okay, you might have to do other things also. If you have the 6 millimeter space given for you, you can take it. That's all. There is no
Okay,
rule.
so
Yeah.
yes, that should be a design of experiment then. Trial and error we have to use.
Yeah, exactly. Yeah. So that's why I told you, there is no, complete theory here. You have to do a lot of theory, experiment yourself with the simulation, come back and forth. Then only you can come back to the final design. It takes a lot of effort. Yes.
Okay.
But the steps
And
are
sir,
this. Yes.
Okay, sir. And what about this lookup table that we have used by using that Agilent Momentum EM simulator? So
yeah,
it must not be in a DM poser, na?
No, this is from this book. No, I told you this filter design book you can look into.
Okay,
microstep filter design by
Yes,
Rafat
microfilters for
Richard
that.
Mansur. Yeah, you can also go into this. It's a very good book for filter design.
Okay, sir. Okay.
Yeah.
So, sir, can we get these slides?
Slides, no, I cannot provide. But the video is there, right? Yeah, video is there, so
Yes,
you
sir.
can. Yeah.
Okay. Okay, sir. Okay, I appreciate.
Okay. Yes. Okay, so so today we'll close and please do the assignments yourself. And
Okay, sir.
yeah, if you really want to do, I have not asked specifically for a bandpass filter design with microstrip line, but I will suggest please try these steps yourself so that you can learn. Okay. Yeah. Okay, so see you tomorrow with new theory.